Thank you. Always great to be back in Canada. I've told several people this morning to come to an event like this, I need to come to Canada. We have nothing like this in the US at this point. I've always been impressed by the level of interest in hydronics from Canadians. Over the years, we've done several sessions up here and consistently had really strong interest, good turnout. So my hat is off to you. So thank you for having me. Just so I have a feel, how many contractors do we have here today? Those that turn the wrenches. We got quite a few. How about engineers? Some engineers here today, okay. Wholesalers? All right. And coming from the United States, I've got to ask, are there any attorneys present this morning? No, okay. I'm going to stand up front here because I'd like to point to things. And, I could look at that screen, but I could also point to things up here. So bear with me. I'm going to have my back turned to you a little bit. The topic that we're going to take a look at this morning is adding air-to-water heat pumps to existing hydronic systems. Again, how many here are aware of or have worked with, maybe I should say have worked with, air-to-water heat pumps? Anybody? How many are interested in air-to-water heat pumps? Quick show of hands. Look at a lot of interest in that. And we see that interest building year by year, and especially this year. I'll show you a slide. There were quite a few new rollouts in the category of air-to-water heat pumps at the AHR show back in January. And I think some of the initial market is going to be where we take heat pumps, air-to-water heat pumps, and we add those to existing hydronic systems. Part of that is going to be driven by electrification. Up here, I know you have carbon taxes. I know your fuel prices are going up pretty steeply. So from an energy cost standpoint, certainly air-to-water heat pumps bring the possibility of cooling to the hydronics market sector. That has always been kind of an Achilles heel with hydronics. What do I do about cooling? And with air-to-water heat pumps, you can do chill water cooling. We're going to talk about that more this afternoon. So let me get right into it. Again, what is an air-to-water heat pump? It's a pretty simple device. Heat pumps have been around for decades. Obviously, the air-to-air heat pump is probably the best-known form of that. I'm sure many of you are familiar with ductless mini-splits, and even before that, companies like Carrier and Trane and York were doing it. We're going to talk about how they perform. Like most heat pumps, the warmer the source of the low-temperature heat, and the lower the load temperature, the better these heat pumps are going to perform. It is important to understand that current generation heat pumps are going to perform better with low temperature hydronic systems. I'm sure many of you know that, but we're going to emphasize that. We're going to take a look at seasonal performance characteristics. When we look at things like heating capacity and coefficient of performance on heat pumps, we're looking at graphs usually, and we're looking at what I'll call instantaneous performance. If we have a certain water temperature and a certain air temperature outside, we have a certain heating capacity and a certain COP. But obviously those conditions change over the season. So how do we integrate and blend all that together over an entire season? And I'll show you a project we're involved in that will give you some idea of what the seasonal coefficients of performance are. And then we're going to look at why keep the boiler in the system? What's the justification? Again, in the course of my business, I've talked to quite a spectrum of people. I've talked to people that absolutely think fossil fuels are the scourge of the earth. I don't agree with that. I think there's certainly ample opportunity to integrate heat pumps along with fossil fuel, and I'm hoping to show you, justify why keep the boiler in the system, especially if it's an existing system, the boiler is already there. We're going to look at some piping arrangements, and then we'll look at some example systems. Okay, now before we get into the details, this is important, okay? Don't try to add a heat pump to a hydronic system without first understanding hydronics. We're just talking about that this morning. I think one of the fear factors in the industry, not you folks understand hydronics in general, but outside of this sphere of people, you've got people that really don't understand hydronics. They think about when you say the word hydronics, they might think, oh, that my grandfather had that kind of a system. It has cast iron radiators and this big box that smells down in the basement. And they're thinking it's old, it's antiquated, it doesn't apply anymore. Well, modern hydronics is absolute state of the art. But you need to understand how to size a pipe, how to size a circulator. Where does the expansion tank go? How do you get the air out of the system? The Hydronics 101, which is going on upstairs right now, again, I'm sure many of you have already are accomplished in that. But again, as we get people interested in air-to-water heat pumps in particular, don't try to do an air-to-water heat pump system without understanding the basics in hydronics. Adding a heat pump to a poorly designed or installed or poorly maintained system is not going to fix the problem. And again, these are pretty common sense no-brainers, right? And yet, I've watched over the years, and I've been doing this for about 45 years now, I've watched people look at a new heat source in particular coming into the industry, whether it's a solar collector or whether it's a biomass boiler, thinking that this is the panacea, this will make everything right in the system, and they take that brand new product and they install it into a marginally performing system and they get disappointing results. So it is important to understand and evaluate, if it's an existing system, evaluate the system first before you just plug the heat pump into it, okay? So, with that in mind, anybody know what that is? That's about $500,000. That's a Ferrari 10-cylinder engine, okay? Beautiful piece of hardware, very high performance. I think it's up around 800 horsepower. So let's say I'm going to get involved with NASCAR racing, right? And I'm going to go to Italy and buy one of these engines, and I'm going to bring it home, and I'm going to put it in this. Cub Cadet lawn tractors, okay? Anybody know what that symbol is right there to the right of the Cub Cadet? Anybody? Is not equal to that, okay? And yet think about what can happen very easily. Somebody goes out, buys a brand new air-to-water heat pump, and they just cut out, maybe they cut out the boiler, maybe they put a couple T's in next to the boiler, and they put the heat pump in and wire it up and so forth, turn it on, and the thing short cycles or it trips out on some other condition. Why is that happening? Because they haven't looked at evaluating what I call the balance of system. And the balance of system is everything other than the heat pump. The pipes, the circulators, the expansion tank, the heat emitters. They need to look at all that and make sure that you are building a system where the heat source and the balance of system are compatible, okay? So, for those that haven't had any exposure to air-to-water heat pumps, I want to do a very quick summary here. Again, we talked about ductless mini splits. They're everywhere. You can buy these on eBay. You can probably buy them on Amazon, okay? Certainly they're out there. They're kind of a plug-and-play technology. They work, okay, but they're a box on the wall that blows warm air in the winter, cool air in the summer, and you have lots of the line sets going from the outside to the inside. And I'm sure everybody in this room is familiar to some degree with geothermal heat pumps. We put piping in the ground, or maybe we draw water from a big lake or a well, and we extract low temperature heat out of that water and put it through a refrigeration cycle, bring the temperature up, and distribute that heat either with forced air or water-to-water heat pumps, again tying into hydronic systems. But air-to-water is new in this market, very new in this market. So we still have that person with the question mark thinking, what does an air-to-water heat pump do? I can tell you that there are a lot of people out there writing energy rebate programs in our United States at the state level or the federal level or up here probably at the provincial level that really don't understand what an air-to-water heat pump is. And they need to. And that's slowly progressing in the positive direction, I will tell you that, okay? So basically, if you wanted to explain an air-to-water heat pump, say, well, you know, we all know what air-to-air heat pumps are, right? Ductless mini splits or a central ducted system. and a smaller amount know what a geothermal water-to-water heat pump is. So what we're doing with an air-to-water heat pump is we're using the outside air as the source of the low temperature heat. So we're refrigerating outside air, even air that is below, you gotta be careful there, below 0 degrees Fahrenheit. What's that, about minus 16 or whatever up here. And then we're taking that higher temperature heat, we're putting it into a stream of fluid. Usually it's going to be a mixture of water and antifreeze because the heat pump is sitting outside. We don't want it to freeze up if there's a long-term power outage. And then we're going to distribute that warm fluid through a hydronic distribution system. So again, it's really just a combination of air source technology with hydronic load technology. And there are several products today that you can take a look at. It's interesting that even though in North America, air-to-water heat pumps are relatively new, in other parts of the world, they're very, very commonly used. Asia is probably one of the biggest markets, China in particular, and as well as the European market. Those are both much larger hydronics markets, which explains to a large extent why air-to-water is more common. This is a publication that comes from Japan, and it's similar to publications we have. It's kind of a publication that keeps track of market statistics. And they put out an issue every year that focuses on how is the air-to-water heat pump market globally changing. And the latest statistics were from 2022. Globally, that went up almost 22%. So that's a strong increase. Almost 5 million air-to-water heat pumps were installed, or I should say sold, in 2022. This is a graph. It's a little hard to read it in detail, but the red bars that you see on that graph, that's China. That's the market in China alone. Everything else is lumped into the other bars there. Don't look for a bar for Canada or the US. It's too small to put up there right now. But you'll see in Europe, it's a strong market. I do have some other statistics here. You can see, again, China, 2.3 million air-to-water heat pumps. Japan, almost 500,000. And then typically the strong hydronics market in Europe. France, Germany, UK, several hundreds of thousands of heat pumps. So it's becoming very common over there now. There are programs that are pushing heat pump technology, pushing away from fossil fuels in the European market. That's to some extent responsible for that market growth. And just the fuel cost in general, very expensive. So that market is growing. Now, internally, this is a very simplified diagram. If you know anything about heat pumps, you know in a basic refrigeration cycle, you've got 4 components. You've got a compressor, a condenser, some kind of an expansion device, and then an evaporator. And of course, you can change the physical configuration of those components to, for example, extract heat out of air instead of extracting heat out of water. All right, so, and that first diagram that's up there, again, let's just follow it. Let me start up at the top. We've got some kind of an air handling section. We've got a coil, aluminum fins, copper tubing, there's refrigerant in the coil, and we have either 1 or 2 fans that blow outside air across the coil. This is where we have cold refrigerant, and we're causing that refrigerant to absorb heat. The refrigerant is colder than the outside air under all conditions. So you can have very, very cold refrigerant. It evaporates as it absorbs that heat. It comes down, and let's see, goes through the reversing valve and then into the compressor. The reversing valve is just basically giving it a U-turn, sending it into the compressor. When we compress any gas, we bring the temperature up. We're going to send a high temperature gas over to this heat exchanger. This heat exchanger is functioning as the condenser of the refrigeration cycle. We're causing the refrigerant to give up its heat to a fluid. It could be water, but as I mentioned earlier, if the heat pump is outside, it's typically going to be a mixture of water and antifreeze. And then you'll see the piping here that brings warm fluid from the return side of the heating system in the house, brings it out, sends it through the condenser, absorbs heat, and then you have the warmer stream going back into the house. And then finally, we've got some kind of an expansion device. Takes the higher pressure refrigerant, drops its pressure, which drops its temperature, sends it back to the air handling portion up here, and the cycle repeats. So this is a very basic 4-function or 4-component, actually 5-component, because I'm showing a reversing valve here. You can build a heat pump that is non-reversing. You would leave the reversing valve out, but pretty much everything on the market today is going to come with a reversing valve. That's an important point. When you buy an air-to-water heat pump as a heat source for a hydronic heating system, you're buying a chiller at no extra cost. That reversing valve is in there. So you can design a system for both space heating as well as cooling. And the only difference here is the path of the refrigerant. The reversing valve just, in effect, reverses the function of the evaporator and the condenser. Now we're absorbing heat from the liquid, chilling it down, and we're dumping the heat outside through the condenser unit. Okay? Now, as you look at the products that are around here today and you pop the hood and take a look inside, you're going to see more than just these components. You're going to see sensors. You're going to see, in many heat pumps today, what is called enhanced vapor injection. There's another heat exchanger that can get that refrigerant temperature much, much lower than just a standard system like this. You're going to see control boards and so forth. But fundamentally, these diagrams still apply. Okay. Now, by the end of this year, this was a major rollout year at a very large trade show we have down in the States. I still call it the ASHRAE show, but it's AHR show. Anybody here go to the AHR show? I'm sure some of you have. It's 2,000 plus manufacturers. It was in Chicago back in January. And I always like to walk around and look at, what's the new products that are coming in. And one of the distinct trends that I saw is that several companies, well-established companies in the hydronics market, well-established boiler suppliers, chose to get into the air-to-water heat pump market, and the rollout of the product was this year. Some of those products are on the market. You can buy it today. Others are coming by the end of this year. Others will be out very early in 2025. But if you look at the names that you see up there, I'm sure you recognize pretty much all those names. Here are some of the products that were in the market for several years. Intertech Space Pack, Aramec up here, and so forth. These products have been on the market. I'm going to say at least, some of these products have been on the market at least 10 years. Okay? But just at the show, this was the rollout. And again, you see, if you look through some of the names there, several of the major boiler manufacturers and so forth. So right now there are, by my count, at least 18 companies that have product or soon will have product in the North American market. So product availability is not an issue. It's not really an impediment to adoption. Many products that were out previous years are running on R410A refrigerant. As many of you know, R410A is already on its way out. R32 and R454B are coming into the market as replacement refrigerants. In the long term, I think you'll see R290 propane and CO2. These are going to allow us to get to higher temperatures. Okay? Now, let's talk about, again, the different kind of physical configurations of air-to-water heat pumps. We've got self-contained, or what are commonly called monoblock heat pumps. A monoblock heat pump puts everything in one box, and it goes outside. So all those refrigeration system components are outside. The controls are inside the box. The fans, everything is outside. It comes from the manufacturer pre-charged with refrigerant. So you don't have to have refrigeration skills or tools to install a monoblock heat pump. Basically, you bring line voltage out to it. You bring some control wiring out to it. The control wiring can be pretty basic. But there's a couple ways you can configure these systems. In climates like Canada, and even quite honestly in most of the United States, most manufacturers of monoblock heat pumps are going to require antifreeze, and they're doing it to protect the unit against freezing. Now, some of these units will do things like they'll turn on circulators when the outside air temperature drops below maybe 40 degrees Fahrenheit, even if there's no call for heating. They're doing that to try to keep those components warm. But what do you do when it's well below zero and you have a 2-day power outage? Okay? You're not going to run out there and drain the water out of the unit, and it could freeze under those conditions. So you're going to find that with monoblocks, it's going to be common to have antifreeze. The other thing that's interesting about using antifreeze with these heat pumps, it's not just about the heating cycle. It's also about the cooling cycle. Under low ambient, low outdoor temperature conditions, if the unit is operating and cooling, some of that refrigerant could get cold enough in the evaporator to actually start to form ice in the evaporator. So antifreeze is being required for freeze protection in heating mode, but also freeze protection in cooling mode. Now, the two diagrams over on the right there, one is, the top one basically uses antifreeze in a whole system. And you can sell that as kind of an upgrade, okay? We're protecting the entire hydronic system against the long-term power outage. One of the terms that you probably read a lot is it's a popular term today, it's called resiliency, okay? And it's a good idea. Resiliency is about what happens when things go wrong. How does the system survive? And certainly putting an antifreeze solution that can protect that hydronic system from days, if necessary, of sub-freezing conditions is one form of resiliency. Now, the other thing you can do is put a heat exchanger between the heat pump and the balance of the system, and you would use antifreeze between the heat exchanger and the heat pump. So this is a closed loop right here with an antifreeze solution. So you've got a circulator, and you've got the other trim, air separator, expansion tank. You really should have a pressure relief valve in any closed hydronic circuit that has a heat source in it. And then the heat exchanger is the interface to the water and the balance of the system. Now, I've done this, it works, but there are consequences to doing this. Anytime you put a heat exchanger in a system, you have to have a certain temperature difference between the hot side and the cool side to drive heat at some known rate or expected rate through the heat exchanger, okay? And you can size the heat exchanger for differences in that temperature difference. We call that the approach temperature difference. That's the difference between let's say the hot antifreeze solution coming in here and the warm water leaving the other side of the heat exchanger. If you're going to use a heat exchanger, I would suggest to you that the approach temperature difference be no higher than 5 degrees Fahrenheit, say 2 degrees Celsius. We don't want to have undersized heat exchangers. That is going to become a huge thermal bottleneck in the system. What's going to happen is it's going to force the heat pump to operate significantly warmer than it would otherwise operate if the heat exchanger wasn't present. What is that going to do to thermal performance of the heat pump? It's going down. You can look at the curves. Not only is the heating capacity going down, the coefficient of performance is going down. Now, I understand if you have a very high volume system on the other side, maybe you've got some big storage tanks or something like that, maybe you don't want to buy 100 or 150 gallons of antifreeze. You can use a heat exchanger in between. Know that when you put the heat exchanger in there, you have certainly the cost of the heat exchanger, you have the second circulator, you have the other trim here, okay, and the labor to put it all together. You're kind of balancing that cost-wise against antifreeze. You know, if you're going to put 50 gallons of propylene glycol in, I don't know what it's selling for up here now, and like everything, it's higher than it used to be. So either approach can work. From a pure thermal performance standpoint, I prefer the upper diagram. Put antifreeze in the entire system, eliminate the thermal penalty of the heat exchanger, and keep the system simpler from a component standpoint. Now, there's another physical configuration. We generically would call this a hydro split. It's the combination of a monoblock heat pump outside along with an indoor unit. And that indoor unit, think about the size of a ModCon boiler, all right? The fluid that is going between the outdoor and the indoor unit in a hydro split configuration is a mixture of water and antifreeze. It's not refrigerant, okay? The indoor unit is typically configured to reduce your labor on site. So the circulator, the expansion tank, the controls, purging valves, things like that that you might purchase as separate components and assemble on site, manufacturers that are providing this are putting that together as a pre-engineered, pre-assembled system. So basically you can put the indoor box on the wall, and as you can see in the diagram here, basically you run piping out to your load, your space heating load or your domestic hot water load, as well as piping going out to the outdoor unit. And then you would charge the entire system with a mixture of water and antifreeze. So that's a hydrosplit configuration. And then one other configuration is a split system. Now, this is similar to what you have with residential AC or even ductless mini split. You have an outdoor unit, you have an indoor unit, but you're running refrigerant between the indoor and the outdoor units, just like you would with a residential AC system. So to install the split system, you do need to have some basic refrigeration tooling. In the States, you need an EPA certification. I'm sure you need something up here as well. And you need the skill set to do it. It's not hard. It can easily be learned. I don't want to discourage people that have done primarily just hydronic systems from getting basic refrigeration tooling and skills. Because even if you're installing monoblock systems, down the road you may have to service a refrigeration component in a monoblock system. You should know how to pull the charge out, test it, refill it with refrigerant and so forth. But this is typically, we call this a DX or a split system. Okay, so that's 3 different physical configurations. They're all available from different manufacturers. And I think as the market progresses, you'll see manufacturers that may have entered the market with just a monoblock configuration eventually offer a split, and vice versa. Okay? Now, performance. I mentioned earlier, anything that you can do as a hydronic designer that will bring water temperature down is going to improve the heating performance of the heat pump, okay? And I'm just showing a typical set of curves here. What we're looking at on the bottom axis there is outdoor temperature versus heating capacity. And this is a nominal 4-ton, 48,000 BTU per hour heat pump. And you have to rethink, when we talk about heating capacity as a heat pump, don't think about a heat pump as a boiler, okay? A boiler's a pretty stable heat output. Obviously, a modulating boiler can change, but think, older cast iron boilers, you've got a pretty stable heat output whenever that heat source is on. With a heat pump, you can see from these curves, the capacity at minus 10 degrees Fahrenheit is down in the range of maybe 15 to 20,000 BTUs per hour. If it was 70 degrees outside, we're what? About almost 3 or 4 times that capacity. And obviously, as you go through a heating season, you're sliding all over these curves from an outdoor temperature standpoint. And then the 3 curves up there just represent leaving water temperatures, okay? In general, with heat pump theory, as the water temperature goes up, the heating capacity goes down. Now, with some modern refrigeration systems with enhanced vapor injection, you'll actually see a slight increase in capacity as the water temperature goes up, all right? But there's another graph that's important, and that's the coefficient of performance. If you've never heard of coefficient of performance, very simple. It's a ratio of the heat output from the heat pump divided by the energy you put in the heat pump to make it operate. We'll put electrical energy in. We could convert watts over to BTUs per hour and then divide that into the BTUs per hour heat output, and that gives us a number. And the higher the COP, the more efficient the heat pump is. So again, if you look at those curves, the blue curve is when we have 110-degree water leaving the heat pump. The lower curve there, the red curve at the bottom, that's for 130. So you can see at any given outdoor temperature, the warmer the water temperature leaving the heat pump, the lower the coefficient of performance, and also as it gets colder outside, the COP does drop off as well. Now, you can't control the outdoor temperature, but you can, as a designer, do everything possible to bring the water temperature down in the system. And I believe we've talked about that. I know we've talked about it in articles through HPAC. We've talked about it at previous Hydronic Summits. There's basically two categories of modification that you can use to bring down water temperature. You can decrease the heating load of the building. If you add insulation, if you improve the windows, if you reduce air leakage, anything that is weatherization related that brings that heating load down without touching the hydronic distribution system will allow lower water temperatures. And there's some simple formulas to calculate it. Basically, the more you take the load down, the lower the water temperature requirement at design conditions is going to be. That's one approach. The other approach is you can add heat emitters, okay? We might have a baseboard system. We could add more baseboard to it. We might have a baseboard system. We could add panel radiators. We could add fan coils. We could add some areas of radiant panel heating, okay? It doesn't all have to be the same heat emitter type. The general idea is the more surface area you have collectively in your distribution system, the lower the water temperature is going to be. Now, that typically is the harder approach because now you're cutting pipes, okay? And obviously you're upstairs, you're not in the boiler room. You're upstairs moving furniture and cutting pipes and so forth, but it is a viable way to bring the water temperature down. So, in general, with heat pumps, if you're trying to explain this to somebody, it's very simple. If you look at the outside air, that's the little blue cloud here. This is the water that you're heating to send through your heat emitters. Anything you can do to bring those two clouds closer together is going to improve the performance of the heat pump, okay? Again, with an air source heat pump, you can't really do much with the outside temperature, but you can effectively take that temperature and bring it down through, especially in new systems. If you have a clean slate, design around low water temperatures. One of the guidelines that I have used for years, I suggest it to people, it's not a code, it's not a ASHRAE standard or anything. I would tell anybody today, regardless of whether you're using heat pumps or boilers or whatever it is, at design load conditions, your water temperature should not go above 120 degrees Fahrenheit, okay? That keeps your system relevant to heat pumps, mod-con boilers, any kind of heat source. And I also want you to think about the concept of future-proofing your hydronic system. Hydronic distribution systems, properly designed, properly installed, reasonably maintained, how long will they last in a building? Decades. Decades. We've seen hydronic systems well over 100 years old, okay? It's a long-term value proposition to your customer. Explain that to them. Remember, our customers today, clients or homeowners, how long does a dishwasher last? How long does a refrigerator last? How long does a clothes washer last? You know, there's 10 years, maybe 15 years if you're lucky, right? That hydronic distribution system is going to last a long time. Now, it may not, the original heat source probably isn't going to last that long, okay? If it's a modern boiler, maybe it's 15 years. Get lucky, 20 years, okay? Cast iron boiler, they can last for a long, long time, easily 30, 40 years, okay? So the distribution system is going to stay in the building. It's probably going to get a second heat source or, a new heat source, a replacement heat source. Maybe another one after that. But you're designing around a long-term value proposition. What you don't want to do today is create a hydronic distribution system that 15 years from now has to be extensively renovated because the heat source that we designed it around today can't produce the water temperature, or our politicians say, no, you can't use that heat source anymore. You think that's going to happen? I don't know. I don't know. And I promise I'm not going to deviate into politics here, but it could happen. So if you design around a water temperature of 120 degrees or less, regardless of what that initial heat source is today, you're future-proofing that system for the, to be upgraded in the future. And explain that to people. We've had clients over the years, why do you go to bigger panel radiators? Somebody else said, oh, you could use a radiator half that size. And you could. We're doing it because we're looking down the road beyond that initial purchase. And many people will see the value in doing that. Okay. Now, one of the projects I was involved in a couple years ago, in New York State, we have an organization called NYSERDA, New York State Energy Research and Development Authority. And they have been involved with heat pumps and promoting heat pumps for a long time, primarily air source heat pumps and geothermal heat pumps. And I've been trying to build a case with them for air-to-water heat pumps. And I'm encouraged. Things in government move pretty slow, but I do see light at the end of the tunnel. And one of the projects that we were asked to do, can you build us a simulator that will give us a reasonable idea of how an air-to-water heat pump will perform against, let's say, a ductless mini-split? So we built a program that would do that. And I just want to show you an example of one of the simulations we did. Now, again, any simulation has assumptions built into it. One of the assumptions that we wanted to build in, we did not want the heat pump to operate above 130-degree water temperature. Many of the heat pumps that are on the market now, especially R32, R454B, they can go to higher than 130 degrees. COPs do go down when you push them up to their limit. But we did limit the water to 130 degrees, and we used outdoor reset control on the water temperature requirement. That's important. You don't need, even if you design around 120 degrees, as I just mentioned, at design load, you're only at design load like 2% of your hours in the heating season. In many hours, you can be much lower than that, and the heat pump is going to benefit from that lower water temperature. We also built in a pretty aggressive defrost model. Now, air source heat pumps will build frost on their outdoor coil, whether it's an air-to-air heat pump or an air-to-water heat pump. How much frost depends on humidity, it depends on temperature, obviously depends on the run time of the heat pump. But if you look at a heat pump, you'll see, at times, you'll see the coil completely frosted up. And the internal controls in a heat pump will sense that, and they will basically put the heat pump, they will reverse the refrigerant. They'll temporarily put the heat pump in cooling, which sends heat to the outdoor unit, which quickly melts the frost. Then the fan will come on and it'll kind of blow the air off the coil, and then the unit will switch back into heating. When you do that, you're taking energy that the heat pump put inside the building and you're taking it back out. It's definitely a parasitic function, but it's a necessary function. So we built a defrost model into it, and I put the conditions that are up here. It was a nominal 4-ton rated, low ambient, which means it's using an enhanced vapor injection refrigeration system. So it's capable of operating at sub-zero Fahrenheit conditions. The building envelope, it was a 36,000 BTU per hour load, -9 outdoor temperature, 70 degrees inside. We assumed a steady 2 kW internal heat gain. The reason we put internal heat gain in there, it offsets some of the heating load, okay? And walk around your house, look at how many of those little transformers are plugged in, and just televisions. When you turn the remote off, does it kill the power to the whole unit? Doesn't. So you've got internal heat gain from appliances, from people, from sunlight, from lights, okay? So we built in a slight adjustment for that. We also ran the simulation with and without domestic hot water loads. And the domestic water load was 60 gallons a day, heated from 50 to 120. And then what we did with our simulation tool, we ran it for different design load supply water temperatures, all the way from 100 degrees up to 180 degrees. Now, you're probably thinking, you just told me you didn't let the heat pump go over 130. We didn't. Anything over 130 has to come from auxiliary heat, be it electric or a boiler, whatever it is. So the COPs and so forth that you're going to see in the contribution of the heat pump is from 130 degrees down in terms of water temperature, okay? So let's start over here. These are just the supply water temperatures at design load, okay? Seasonal average coefficient of performance without the domestic water load. Let's say it's just space heating only. So we range from about 2.8 up, going down from about 2.8 to about 2.6. That 2.6 is still a respectable COP. It's 2.6 times less electricity than an electric boiler would use, okay? But you can definitely see the COPs are going down as the water temperature are going up. The next column here, this is the percent of the space heating load that was met by the heat pump, okay? Now, remember, this is a nominal 4-ton machine, that's 48,000 BTUs per hour, going into a 36,000 BTU per hour house. And you might say, well, gosh, you're grossly oversizing that heat pump. If we were talking about boilers, I would agree with you. But remember, that the reason I use that word nominal is because those curves, you're always moving in terms of your heating capacity and your coefficient of performance. Personally, I don't see a problem with putting a 48,000 nominal heat pump into a 36,000 BTU power load in a hydronic context, okay? Because we can use that heat pump. We could charge a buffer tank with it, for example, or it may be a heat pump with a variable speed compressor. We can adjust the capacity down as we have zones turning off. But you can see here, at these low water temperatures, we're meeting 100% of that load. Okay, no auxiliary required, but once we start to get up into this temperature range, we start to drop into the 90s. But even in a system that needed 180 degree at design load, remember, full outdoor reset on the water temperature, and this was all driven by what's called bin temperature data. We know this was actually for Plattsburgh, New York. Anybody know where Plattsburgh, New York is? It's way up on the tip, okay? It's an 8,000 degree Fahrenheit day climate. It's a cold place. Now, once we mixed domestic water load in, we actually saw a slight improvement in terms of seasonal COP and contribution to the total load. Think about domestic water heating. It's an annual load. It's a 12-month-a-year load. How's that air source heat pump doing in July and August? It's doing pretty good, because the ambient temperatures are high. Heating capacity is high, and so is the coefficient of performance, and that gets reflected into the mix in the simulation. Now, I made some graphs. There's 3 curves up there. What we're looking at here is what I call annual COP, annual average COP. COP is a moving target. It's always changing as water temperature and air temperatures are changing, but that's what the simulation does. It mixes all those bin temperatures together, coming up with what is the average condition. And you can see in Plattsburgh, that's the green curve here, we go from roughly what? About maybe, it's a little hard for me to see it, 2.8 something, 2.85. And then as we go up in water temperature, you can see consistently our seasonal average COPs are going down. If they were going up, I would question what's wrong with the simulation. That's against the thermodynamic theory. You can see that they definitely start to drop, but roughly between 100 and 120 it's a pretty soft drop. It really doesn't affect it a lot. Once we get to the higher temperatures, our COPs go down. Now, the other curves that are up there, one is for Albany, about halfway down the eastern side of New York State, and the other one's for Brooklyn, down in the city. And obviously, we're going from a very cold climate in Plattsburgh to a cooler climate in Albany to a, I don't want to use the word warm, but 4,500 degree days instead of 9,000 degree days, 4,500 in Brooklyn. And you can see there, we can actually see some COPs over 3. So I make the statement that the COP of a well-designed modern air-to-water heat pump can approach the COP of a geothermal heat pump. I use the word approach. I'm not saying it's always equal. You could come up with a case with a poorly designed geosystem and a very well-designed air-to-water system where the air-to-water might actually have a higher seasonal COP, but you could also come up with a case where you'd reverse that. So I do think it's fair to say that today we have air-to-water heat pump technology that when it's properly applied in a low-temperature hydronic distribution system, we can approach the COPs of what some of the geothermal systems are seeing. And that's a big deal because which one costs more? Obviously, the geosystem is going to cost quite a bit more because of the earth loop. Okay, in our area, a 4-ton earth loop in US dollars easily, if it's boreholes, easily $15,000. Okay, so yes, the geothermal heat pumps do, in general, they can produce somewhat higher COPs. That isn't always the question you should ask. You don't pay for COP, you pay for kilowatt hours. The question you should ask is return on investment. Yes, the geosystem can produce a higher COP. I'm not against that. I've designed many geothermal systems, and they work fine, and there are good applications for them. The question, though, is return on investment. And I do feel that we have the potential with air-to-water heat pumps with good design, proper application, that the air-to-water heat pump market could be a very strong and very healthy, growing market in all of North America. I think there's a lot of potential ahead with air-to-water heat pumps. Now, this is just percent of space heating load that was covered by the heat pump. And you can see relatively flat out to about 140, definitely a difference, though, in Brooklyn versus the other two locations. And then it drops off pretty fast. But look at the vertical axis. We're anywhere from the mid-80s to the mid-90s in terms of the seasonal contribution. So for somebody that's, I think of one person in particular I've interacted with at NYSERDA. Fossil fuel is the scourge of the earth to this person. If we can displace 85 to 90% of the fossil fuel with a heat pump, moving it over to electricity, can you give me that other 5 to 10% with fossil fuel? Could you let me use that? Because there's a lot of benefits in doing that, a lot of benefits to the customer in doing that. So, and that's really what I want to focus on once we've talked about the heat pump performance here. Why keep the fossil fuel boiler? Well, we've already talked about the performance of an air-to-water heat pump. It varies drastically as we have different temperatures. And classic air source heat pump analysis, they'll draw two curves. One is the load curve. That's the blue curve here. In theory, space heating is proportional to the temperature difference between inside temperature and outside temperature, okay? The red curve is the heat pump heating capacity, BTUs per hour from the heat pump. And we know that goes down as the outside temperature goes down and the heating load goes up. So it's inevitable they're going to cross, and we call that the balance point. And in this case, the balance point looks to be what, about maybe 27 degrees? If we put a larger heat pump in, we basically are going to shift this curve up here, and the balance point's going to shift to a lower outdoor temperature. If we put a smaller heat pump in, we're going in the other direction. But in the green area here, the heat pump has more than enough capacity to meet the heating load. and modern heat pumps with variable speed compressors will reduce their speed and reduce their heating capacity to better match that load. In the old days, when you had just an on-off heat pump, you needed a buffer tank. Basically, you're turning it on. It was like essentially turning on a boiler, although, again, the heating capacity would change with outside temperature. Excuse me. The red area is the area you need to be concerned about. That's where the load is greater than the heating output of the heat pump, and we need some kind of supplemental heat. And in general, every project you do up here with current generation air-to-water heat pump, you're going to have a condition, and maybe a short-lived condition, but you're going to have a condition where that heat pump just isn't going to have enough output to match the load. So what do? Well, I've had customers say, well, I'll light the wood stove, I'll light the fireplace. Okay, I've had people say, I'll plug in an electric space heater. Most lending institutions don't want to hear that. They want to know that their investment, their risk in that building is covered by a heating system that can heat the building under any condition. So again, some kind of an automatically called for supplemental heating device. Heat pumps are going to break down. You know, you look at a heat pump, you look at anything today. Your car, your dishwasher, refrigerator. It's unrealistic to say, I'm going to put a heat pump in, it's going to run for 20 years, and there's never going to be a hiccup. Okay? Now, hopefully you have minimal issues with it, but when it goes down, the question you should ask is, or your customer needs to ask really, how quickly can I get it serviced? Let's say it's January and it's, you know, it's cold outside, below freezing, and whatever, something happens to the heat pump. Can I pick up the phone? Can I have somebody there in 2 hours to service that heat pump? That's the question you want to ask. In my area, I live in a rural area of upstate New York. That's not going to happen, especially with an air-to-water, simply because there aren't many air-to-waters on the market right now. Now, I could get a company to come out that's familiar with air source heat pump technology and work on it. Maybe that would be sufficient. I can also call some people locally that if it was a geothermal system, they probably could come. But if that heat pump is going to be down for several hours, if not 2 or 3 days or a week, maybe you're waiting for a part, maybe you have a supply chain issue in getting a part, having a boiler, especially an existing boiler, and I'm assuming that existing boiler was sized so that it could heat the house. The boiler turns on and the heat pump waits to get service. So supplemental heat is one, backup heat is another reason to have that, okay? And again, the backup heat is, if it's a boiler and it was sized to heat the house, you have 100% heating capacity available to you. If it's an electric element, you can have an electric boiler sized for design load. But in a retrofit, you've got to be very careful with that. What's the thing that could be the bottleneck to putting in, let's say, a 30 kW electric boiler in a house that's 100 years old? Service entrance. Is the service entrance, the electric service entrance, sized to handle that capacity? Start doing look at the amp draw, okay? Electric boilers are harder to retrofit in older buildings as a rule, simply because you may have a 100 amp or 150 amp service entrance. Really, with an electric boiler and a heat pump, minimum 200 amp service entrance, okay? So a fossil fuel boiler can run on a much lower amperage. And again, that's the point here, electric service upgrades. If it's an underground service and you're going to take it from 100 amps to 200 amps, you know, you're going to have an excavator, you know, easily $4,000, $5,000, $6,000 in the US to upgrade a service like that today. So again, an existing boiler, or for that matter, even if it's a new boiler, you can run it on much lower power requirements, which brings me to this. You could set up a fossil fuel heating system to run on a very small, I call them tabletop generators, little Honda generator. You can buy one of these at Harbor Freight for $600 US, okay? You could even put in the wiring, and you know, include that as part of the hydronic system installation. The idea is I can keep the fossil fuel boiler and maybe 3 or 4 circulators running as long as I can keep gasoline in that generator. That could go for days, waiting, until the heat pump is back in operation. Of course, today we do have companies like Tesla and Generac. They're selling battery systems. They can work as well as backup. They could keep that fossil fuel boiler going, like depending on the size of the battery, probably for several days, but these battery systems are pretty expensive. Or if you did have an electric boiler as backup, or even if you run it to run the heat pump, if it's a 4-ton heat pump, you're probably going to need I call them a stationary generator, Generac or Kohler or whatever. You're going to need a much larger investment in that generator compared to over here on the left side. And I may try to build a case. If you're doing a new hydronic installation and you're talking to your customers about resiliency and power outages and so forth, why not build this and the wiring right into the project? When you have that power outage, you take this little unit out, turn it on, and you're back in operation during that power outage. Okay, how about the cost of removing the fossil fuel boiler? Now I could take a Sawzall or a set of wrenches and probably disassemble that pretty quickly, but I've got to get it out of the basement. I've got to disconnect it and so forth. The boiler actually is the easy part. This is the hard part and the expensive part. Underground fuel tanks. I've never specified one in any project because I'm afraid of them. When they leak, and in New York State, the DEC is aware of that leak, things can get very expensive very quickly. And I'm not saying don't make the DEC aware of the leak, okay? I'm not trying to break the law, but I'm simply pointing out a leak of a couple hundred gallons of fuel oil into sandy soil. It's very expensive. Fortunately, I haven't had to experience that. I've known of cases. One of the cases that actually involved a tank like this. It was new construction. The heating contractor had put the fuel oil tank put it in, but they hadn't finished the piping on the fuel oil tank. The fuel oil dealer shows up without thinking, puts the hose on the fill pipe, just starts pumping the fuel in. And I think at maybe 300 gallons, they wondered, how come that whistle isn't blowing? How come this fuel still is going back in? They pumped 300 gallons of oil into somebody's basement. Forget it, you're done. The house probably will never be able to be lived in. But just the cost of dealing with old fuel systems, you're adding that to the cost of installing the heat pump. If the boiler is completely shot, I understand. Maybe you're going to replace the boiler with a new boiler. If any of these components in the fuel system are shot, I understand you've got to take it out. But if it still has life in it, and you can look at it and make that determination, leave it in there, because you're not only avoiding these costs, but you have those other benefits that we talked about earlier. Now, looking down the road, if you look at where electrification targets are, and again, I know you have targets here in Canada. We have some pretty aggressive targets in New York State. What's going to happen is peak load. In New York State, peak load has traditionally always been in the summer from air conditioning, especially in the city. But as we look at more and more heat pumps coming into heating operation, there's a projection that somewhere near the end of this decade, we're actually going to shift from a summer peak to a winter peak. And the problem that the utilities face is, how do they meet that peak demand? Do they build more generation? Do they build more transmission lines? Or do they try to do things on the customer side of the equation to encourage shifting loads around? And all I'm showing you here with the blue, this is just a made-up load profile, going from midnight one day to midnight the next day. And it'll vary from one house to another, but typically you'll get a morning peak when people get up and the showers are running and the toaster's running and so forth. You might get a midday peak, or you might get a midday drop, depending on are people in the house running the washing machines and so forth. And then typically you get another peak around dinner time. So imagine we could create an incentive that would take away these peaks and use that energy to basically fill in where that yellow area is. Maybe the utility would offer you lower cost off-peak electricity, or load shifting or load shedding. In other words, I can shut off the water heater, I could shut off the heat pump during certain hours, and there would be some compensation for doing that, either lower rates or there'd be some agreement for that. It's not just that they're taking away your energy without compensation. But if you have a boiler in the system, you have another way to heat the building and shed the load if there is an economic incentive to do that. And I think we're going to see more of this, because this is a lower cost way for utilities to manage growth compared to just building more generation. So look for off-peak, what generically we call time of use rates. Even beyond time of use rates, there's people that are looking at rate structures that will tell you what the cost of electricity is going to be for the next 48 hours into the future. What could you do with that information today? If you knew, starting right now for the next 48 hours, this is the cost of electricity, could you design controls that would optimize the performance of the heat pump and the boiler so that you get the lowest total fuel cost to the end user? Sure you could. Somebody asked me this morning, how is artificial intelligence going to affect the hydronics market? Honestly, I don't know a lot about artificial intelligence, but to me that makes sense. If you know what that price is going to be, if you can predict weather patterns into the future, and those weather patterns are largely the driver for those electrical prices, then could we use artificial intelligence to optimize the mix of fuels? And sure we could. So, I look at this, I'm very optimistic about the potential for what I'll call a dual fuel system, where we have different fuels available, different energy sources, different rates, and if we use something like artificial intelligence to optimize that mix. Now, you may have a system, and I point to indirect water heaters as a good example of this. For years, indirect water heaters were put out with the idea they'd be connected to boilers. And if you look at some of the rating tables, look at the water temperatures that these ratings are based at. It's common to see 180 degrees Fahrenheit, and sometimes you'll see performance at 200 degrees Fahrenheit. Bottom line, indirect water heaters were designed around high temperature supplies from boilers. So what happens if we take one of these and we drop it into a heat pump system, especially if it's been in place for 10 or 15 years, and add to it some scale on the coil because you've got hardness in the water? What's going to happen? You're going to have a problem. You're probably going to short cycle the heat pump because the heat exchanger in that tank simply can't dump the heat that the heat pump is giving it into the domestic water at the same rate that the heat pump is supplying it. Okay? So you could replace the indirect water heater. You could get an indirect heater with a much larger coil. You could go to an external braze plate heat exchanger. Or maybe it just makes sense to shift that indirect over to the boiler and not even have the heat pump work on it, especially if it's a marginally performing indirect to begin with. Okay? It might make sense to do that. And you certainly could design a system that when there's a call for domestic water, the boiler gets the call versus the heat pump. You could exclude the heat pump from that. That may be another reason to keep the boiler in the system. And again, time of use rates. I put a couple rate structures up over on the right. One is from Guelph down the road here. The other is from in the States in Nebraska. And you can see there's actually more than two rates. There's what I'll call an on-peak rate, which is the tall bars here, okay? Then there's a shoulder rate. Shoulder rate is between the on-peak rate and the off-peak rate. And different utilities have different structures on these rates, okay? It's a complicated thing from a utility standpoint. They have to look at their generating assets. They have to look at their load patterns. They have to look at how can they buy electricity from other utilities and so forth, what's the wholesale cost. But when you have a rate structure like this that goes from under 5 cents per kilowatt hour to over 16 cents a kilowatt hour, you can certainly leverage that. You could leverage it with an electric boiler. You could leverage it with an air-to-water heat pump, okay? And if you do need heat during an on-peak period and you have a boiler, it may make sense to operate the boiler and simply leave the heat pump inactive during that on-peak period. Now, this is another question that comes up. Let's say I'm going to put an air-to-water heat pump in, but I've got a cast iron boiler and it's 15 years old. Should I replace it? Because I know the cast iron boiler is mid 80% efficient, and I know I could get a ModCon boiler that has the potential, and I stress that, it has the potential to operate in the mid 90% efficiency. So I ran a case, and some of the numbers here are my local numbers, and I ran this back in the spring, so they may not apply up here, but I want to show you the methodology. It's pretty simple, all right? So again, I'm putting in this state-of-the-art heat pump. Should I upgrade the boiler? So what's the remaining life expectancy of that boiler? And again, cast iron boilers, I've got 2 cast iron boilers. They're both at least 25 years old. They look like the day they came off the crate. They're running beautifully, okay? Yes, they've been serviced, but nothing major. We change the nozzle on the oil burner, we clean it, and change the oil filter and so forth. If it's a 15-year-old cast iron boiler, it's in good shape. It's got a lot of life left to it, okay? What's the efficiency? And again, I put down mid-80s for older. I don't really like the term non-condensing boiler because every boiler can condense given the right conditions. I use the term conventional boiler, a boiler not intended to operate with sustained flue gas condensation, okay? Typically, you're in the mid 80% range, and again, ModCon boilers, you can be up in the mid 90% range with low water temperatures for the distribution system. What are the fuels available? Where I live, I can't get natural gas. We can get fuel oil, we can get propane, we can get electricity, we can get firewood, okay, but we can't get natural gas, so that's going to bear into the decision. What's available for supplemental or backup heat? Okay, again, based on fuel availability, is the service entrance big enough to handle an electric boiler? Okay, and the cost of removing the boiler and the vent system. If I'm going to upgrade to a ModCon boiler and I'm going to take out a fuel oil system, the tank, the boiler, the interconnecting piping, the flue and all that, what's the cost of doing that? And I put down easily $8,000 US to do this. I'm probably being low with today's cost on things. But just to buy the ModCon, install it, remove the other boiler, easily $8,000. So the question is, can I get that $8,000 back or even more than $8,000 by going to that higher efficiency? Okay? So again, I built a case around this last spring. Again, it's a house, 2,500 square foot house, 20 BTUs per hour per square foot. Design load is 50,000 when it's 0 outside. Little bit of internal gain, 1 kW. It was in Syracuse, in mid-upstate New York, not that different from where we are climate-wise. 4-ton, low ambient, air-to-water heat pump. Distribution system is 170 at design load, so it's probably a baseboard system, okay? Existing boiler, 60,000, AFUE rating was 85%. The new boiler, 60,000. Well, let's use an AFUE of 95%. Domestic water load, again, 60 gallons a day, 50 to 120. The cost of the fuels last spring, based on NYSERDA data, fuel oil was right around $4 a gallon, and propane's pretty expensive in upstate New York, just over $3 a gallon.
And we're going to use outdoor reset control on our system. And we do factor in defrost performance degradation on the heat pump. Now, I know you can't read it because I can't read it. This is part of the simulation software that we built. But I just want to point out, we're running this based on the assumption of 170-degree water at design load, okay? These are our results here. Total heating energy required for the season, and these are in million BTUs. MMBTU is a million BTUs. So we had space heating required about 111 million BTUs. Domestic water was about 13 million BTUs. And the auxiliary heat source, whatever it is, had to deliver about 9.3 million. So this is a key idea. Yes, a ModCon boiler has a higher efficiency than, let's say, a conventional boiler when it's properly applied. But you have to remember, it's only going to supply a small fraction of that space heating energy. Think 10%, maybe 15%. So the difference in efficiency, it's not the same as if you were completely switching from a conventional to a ModCon boiler and getting all your space heating energy through that boiler. You're only going to get 10 or 15% through that boiler. And that really is what sets the economics, okay? The heat pump was delivering about 92% of that total space heating energy. So now we start doing the numbers. So if we take $4 a gallon fuel oil at 85% efficiency, and we convert it to dollars per million BTUs, it's about just under $34 per million BTUs. That's supplied to the building, okay? So we've already factored that 85% efficiency into it. ModCon boiler operating on propane at $3.14 a gallon is actually a little more expensive. That's because the cost of propane is pretty expensive. So even with a 95% conversion rate, we're at about $36, okay? So now, since we know the auxiliary heat source has to supply 9.3 million BTUs, the cost to do it, the cost of supplying that energy through the existing boiler, left it in place, $315 per year. If we did a ModCon boiler and we used the $3.14 per gallon propane, it would actually cost more, slightly more, per year, $335. So we actually spent $20 more in fuel in this scenario, and again, your numbers could be significantly different. Plus, we have the cost of installing the ModCon boiler. It's pretty hard to make the case for that based on the economics, okay? How about if we had natural gas? Well, again, NYSERDA data last spring was $1.95 per therm, and if we supplied if we converted that to heat at 95% efficiency, and we supplied the 9.3 million BTUs auxiliary heat requirement, $213 per year. The red text is 85% conversion. The blue text is 95% efficiency. So yes, we save a little. We save $22 a year in fuel. So again, what do you think? Would you spend $8,000, put the new boiler in? Again, I'm assuming the existing boiler has life left in it. You know, that it's not leaking, it's not, you know, you go in there and you see it's a disaster. Yeah, you're going to replace it. But I'm trying to build the underlying case here is the heat pump is doing most of the work. In this case, it was doing 92% of the work. So that existing boiler, even though it's not state-of-the-art, even though it's 85% efficient, it's not doing much of the work. And therefore, the cost difference may not be justified. In fact, here I would say it definitely is not. So, what are the takeaways? Properly sized air-to-water heat pump, in this case, was providing over 90% of the space heating energy. The outdoor reset is critically important. We don't want to force the heat pump to run at water temperatures that are higher than necessary to maintain comfort in the building. You know, I know I'm preaching to the choir on that, but it's important to stress that. We want to keep that water temperature just warm enough to heat the building and keep the burden, if you will, the thermodynamic burden on the heat pump as minimal as possible. So again, the underlying reason for the numbers that we just looked at is that that existing boiler is doing a small part of that space heating energy. And if you're looking at $8,000 plus to upgrade to a ModCon boiler, from a pure economic standpoint, it's not justified in this case. You may do it for other reasons. Maybe you're getting away from fuel oil, you're going over to natural gas. You want to use a ModCon boiler to do it. You know, I'm not saying never install a ModCon boiler with a heat pump. I'm simply saying evaluate what's there to begin with and build the case economically to see if it makes sense to do that. Okay? So let's talk about piping. In general, the concept is we want the heat pump to be piped in parallel with the existing boiler. And really, it's the same if it's a new boiler. We don't want to put things in series. How many have been in projects where you've seen either boilers piped in series or heat pumps piped in series with boilers? Anybody? Yeah, it really doesn't make sense to do that, okay? If one of those has to be serviced and you have to remove it, you've got to temporarily patch up the piping to keep the system in operation. The downstream heat source is always saying higher water temperatures, assuming the upstream heat source is operating. So if you put, the worst case would be to put the heat pump downstream from the boiler. The boiler heats the water, and then the heat pump tries to add more heat to it. You're sending the heat pump higher water temperature than necessary. With this, you've got, if you look at the blue line, it could go either to the heat pump or it could go up to the boiler. And it's really the same concept whether it's if it's a ModCon boiler. Now, look at the upper diagram. There's something present around the conventional boiler that's not present around the ModCon. Anybody see it? They both have circulators, right? There's a little thing right here. It's called an anti-condensation valve, all right? This is a thermostatic valve, and it's designed to protect the boiler against sustained flue gas condensation. What it's going to do, when the boiler first starts and the water or fluid is cool, basically it's going to recirculate the water like this. The cold port of that valve is going to be closed. So we're running the fluid around this loop, and we're removing it. We're uncoupling the boiler from the load. We're bringing the fluid temperature up as quickly as possible because we have very little fluid. We have the full output of the burner heating that fluid. We're getting the heat exchanger above the dew point of the exhaust gases as quickly as possible. We don't need to do that with a ModCon boiler. In fact, we don't want to do that with a ModCon boiler. We want that to condense. But be cautious when you go into an existing system and it's got a cast iron boiler, maybe it's a steel fire tube, maybe it's a copper tube boiler. Those boilers were not intended to operate with sustained flue gas condensation. And remember, when you put outdoor reset control in, you get aggressive with that outdoor reset. You back those water temperatures down, favoring the operation of the heat pump. You're going to create conditions where that conventional boiler, if it's not protected, is going to operate with sustained flue gas condensation. So it is important, it is imperative that you protect that conventional boiler in a retrofit situation. These valves are available from a number of companies. There are other ways to do this. There are injection mixing systems that you could use. Basically, anything that senses the boiler inlet temperature and reacts to it by limiting the ability of the boiler to connect to the load until the boiler is above the dew point of the exhaust gases any configuration of components and controls that'll do that is fine. I'm showing a thermostatic valve because it's a simple device to put in there. But I do want to stress its importance, okay? The heat pump becomes the lead stage. With this piping, both heat sources could operate at the same time. You may have a recovery from a setback. You know, you might have a good example is, let's say you have a garage as a separate zone, and the garage has been off until December, and then you turn the thermostat up on the garage, and you've got floor heating in the garage. That's a lot of mass, and it's cold. You might have both heat sources kick in just to keep up with what the load is there, okay? Either heat source could be the sole supplier if the other is off. So if the boiler's down, the heat pump could operate. No change in piping or valves or anything, and vice versa. Same inlet water temperature going to both heat sources. So if you do have a ModCon boiler, you're getting the lowest water temperature for the best performance. Some air-to-water heat pumps already have the control logic built into them to operate this kind of a system. They can turn on an auxiliary heat source. Some of them are designed to turn on elements in a buffer tank. You could use that same relay to activate the boiler, okay? So this doesn't necessarily imply you have to go out and, you know, put new controls in the system. It's going to depend on the capabilities of the heat pump. Each heat source has its own circulator. I'm a strong proponent. Each heat source has its own pressure relief valve. Anytime you can isolate a heat source, regardless of what it is, pressure relief valve, and you want a check valve. You don't want flow from one heat source going in reverse through the other heat source. It's the same idea as putting zone circulators in parallel. You want to have a check valve in there, either in the circulator or external. I'm a strong proponent of magnetic dirt separation, especially in older boiler systems. If it's a cast iron boiler, if you've got steel piping, iron piping, you probably have some magnetite in the system. You don't want that magnetite on your heat exchanger in that heat pump or the boiler. So do a good system flush. Put some, I call it generically hydronic detergent. You can get it from several suppliers. Clean the system. Put a magnetic dirt separator in as part of the retrofit. And put that anti-condensation valve in. Okay, now here's another piping arrangement. You could do this. Notice, important, the heat pump is upstream of the boiler, and it's a conventional boiler. If the heat pump boosts that water temperature 10 degrees, it really isn't going to affect the efficiency of that conventional boiler to any significant degree. I put this in simply because it might be easier, less involved piping changes compared to putting them both in parallel. So it is a possibility. If you do this, make sure the heat pump is upstream. You always want the coolest fluid available to the heat pump, okay? The rest of those points are all exactly the same. I'm just, in interest of time, going to go through those. Anti-condensation valve, we talked about it. Now, here's another approach, direct to load. Direct to load. This is where we have a single circulator that is pumping the entire system. It's pumping the fluid through the heat pump. It's coming back. You see, I've tied the ModCon boiler in with a pair of closely spaced T's. It's got its own circulator. It can operate as necessary, if necessary, to boost it. And then that flow goes off to whatever the load is. I'm showing some radiant floor circuits. This would eliminate a buffer tank. It's feasible. I've been just in interest of time here. And there are products on the market right now that have direct-to-load piping design. So I would urge you to take a look at it. It's another available piping design. And remember, buffer tanks are for thermal mass, and there's a place for buffer tanks in hydronic systems, even with heat pumps. If you're doing what I call micro-zoning, if you're doing a bunch of panel radiators with thermostatic radiator valves, and you just need a trickle of heat output, the heat pumps basically, I still feel they can't get down as low as what, you need 500 BTUs per hour. Do you have a 410 heat pump that can run steadily and safely at 500 BTUs per hour? If you do, show it to me, okay? But until then, I would still put some kind of a buffering mass in. Now, that being said, when you have a concrete slab with floor heating circuits in it, you've got tremendous thermal mass to stabilize the system. You don't need to have a tank full of water when you've got a concrete slab out there. And I'm going to finish up here with an example that I think is a really good niche market for air-to-water heat pumps. Now, I put down when it's appropriate. One of the things about direct-to-load is you're coming back, you're always going through the heat pump, even if the heat pump isn't operating. Now, if you're using outdoor reset control, and the heat pump is right next to the building, so you have minimal piping between the building wall and where the heat pump is, and you're inside your heat pump, the heat exchanger that is serving as the condenser, it's insulated, you're going to have a little bit of heat loss there. It may not be a lot, and you could say, I can live with that. But what if I'm going to put that heat pump 200 feet away from the building? Would I want to do it this way? Personally, I wouldn't, because I've got a lot of heat loss out there in all that piping, okay? That's where you can go to this next drawing, and all I'm doing here is putting in a couple motorized valves, and when the heat pump is operating, this valve opens. When the boiler is operating, this valve opens. If the heat pump is off, basically you're just doing this, okay? So that's another possibility. It's useful if you're going to have a significant difference in distance between the heat pump and the building. And again, I just want to run through some examples real quick. Cast iron boiler, 3 zones of baseboard. There's the modification. I tried to leave as much of the existing piping in place as possible. Now, obviously, every job's going to be a little different, but look at the relationship between the boiler and the heat pump. They're in parallel, okay? There's the magnetic dirt separator in there. And we're simply coupling to the existing distribution system with a pair of closely spaced T's. What's another way I could couple it right here and eliminate this, the T's, and that? Hydraulic separator. I'm sure there's hydraulic separators in the room you can take a look at. Many of them today have magnetic dirt separation at the bottom. They have a coalescing media for air separation up at the top, and they provide the hydraulic separation. They keep the peace between these circulators out here and these circulators, okay? And, we've talked about hydraulic separation for years. Here's a ModCon going through a hydraulic separator, going off to some floor circuits. Common, simple system. Here's what I've done. Again, I'm trying to leave as much of the system in place as possible. The ModCon and the heat pump are in parallel, and there's a note, I'm running the whole system on antifreeze now, okay? Instead of putting that heat exchanger in. Could you put the heat exchanger in? You could, and you could run everything on the load side of the heat exchanger with water, but you're going to have a penalty not only in the heat pump, but you're going to force the ModCon boiler to run a little warmer as well. And that just takes that seasonal COP down. Now, indirect tanks can give you a challenge. We already talked about it, especially if you have an indirect that's old, the coil is scaled up on it, and it was, the coil is sized around the assumption of high water temperature from a boiler. So here's what I did. I tied the heat pump in. In this case, I showed a split system, just to mix it up a little bit. That's a split system heat pump, but the indoor unit just ties in with a pair of closely spaced T's. Here's the conventional boiler. I've added the anti-condensation valve to it, tied it in, and I would set the controls up. The possibility is to set the controls up so when the indirect calls, just the boiler can supply it. I'm making the assumption that the indirect needs the high water temperature to keep up with the hot water demand rate in the building. Now, again, you might have a system where you've got a much higher performing indirect, much larger coils. Maybe you're using an external brace plate heat exchanger. You could certainly configure it so the heat pump could contribute towards the domestic hot water load. And that, by the way, that's one of the sellable points of air to water versus air to air. Domestic water heating, okay? Show me a mini split that does domestic water heating. Here's a system you might have. It's a conventional boiler with a variable speed injection pump going to some low temperature, high mass radiant, all right? So again, I try to leave as much of that existing system in place. I used a pair of closely spaced T's. Again, I'm showing a split system. The nice thing about the split system in both of these, I don't have to put antifreeze in the system. If it's not already there, or I'm not selling it as an upsell to a customer, this can all be a water-based system, okay? Again, this is refrigerant between the inside and the outside. So this could all be water. And wow, I finished 1 minute over. That's a record. Thank you.